and welcome to Code Disclosed. In this video, I will go through how to construct an irregular convex polygon, how to calculate its side lengths, interior and exterior angles, and at the end, I will show you how to code all of this using MATLAB. Alright, let's start then. First of all, let's understand what polygons are. Polygons are 2D multi-sided shapes with at least 3 sides. There are two kinds of polygons or two types of polygons. They can be either regular or irregular. Regular polygons have equal sides with equal angles. Irregular polygons, on the other hand, they have unequal sides and unequal angles. In this video, I will focus on irregular polygons. For regular polygons, just go to my other video where I went through all of the features of the regular polygon, how to construct it and how to calculate its lengths and its exterior and interior angles. Alright, now for irregular polygons, you can find 3 types of irregular polygons. They can be either polygons whose angles are equal, but sides are not equal, just like these 3 polygons here. They can be the sides are equal, but the angles are not equal, just like here, or neither sides nor angles are equal, just like here. Alright, there is another distinction between polygons I need to focus on here, which is convex and concave. So convex polygon, pentagon in our case here, because we have 5 sides, are polygons where at least one angle is greater than 180 degrees, just like this one. However, concave pentagon or concave polygon in general are polygons whose interior angles are either acute or obtuse. Alright, in this video I will focus on concave irregular polygons in specific. Alright, let's start then. So I'm assuming a very random type of irregular polygon, which is irregular trapezoid, and this polygon has 4 sides and 4 vertices, and each vertex has its own x and y coordinates. This is the Cartesian coordinates. So once we have these coordinates ready, I think it's straightforward to calculate the length or the side length using the Euclidean distance. The Euclidean distance, for example, for LC here, for this side, is the x coordinate of the second vertex minus the x coordinate of the first vertex squared plus the y coordinate of the second vertex minus the y coordinate of the first vertex squared. Using this, I can get the value of LC. The same goes for LD here, LA, and LB. Once we have these coordinates, the x and y coordinates for each vertex, I think it's straightforward to calculate the Euclidean distance. Alright, let's move on now to the angles. Now, let's start with this exterior angles. These are the exterior angles, and we know that the exterior angle is the angle between any side of the shape or of the polygon and the line extended from the next side. So for example, here we have 4 exterior angles, theta 1, theta 2, theta 3, and theta 4. The sum of all these exterior angles for any polygon, whether the polygon is regular or irregular, is 360. Alright, what about the interior angles? So these are the interior angles here, phi 1, phi 2, phi 3, and phi 4. And the sum of the interior angles also for any kind of polygons, whether the polygon is regular or irregular, is always n minus 2 times 180, and n here is the number of the sides. So for example, here for the irregular trapezoid is 4. So 4 minus 2 times 180, I will get the sum of the total internal or interior angles. Alright, I think calculating the sum of all the exterior angles and all the interior angles is somehow straightforward with using very 2 easy equations. However, the question is here is how to calculate the individual ones. So for example, what is the value of theta 1 and theta 2 and theta 3 and theta 4? What is the value of phi 1, phi 2, phi 3 and phi 4? All right, now here's the tricky bit. Let's start with the exterior angles first, and then we can carry on with the interior angles. All right, so the only information we have here is that the sum of all the exterior angles are 360, and I know the Cartesian coordinates of all the vertices. So the tricky bit here is that I know zero information about the amount or the value of any of the exterior angles. The only thing I know is the Cartesian coordinates of the vertices and the sum of all exterior angles. Now, the question here is how to calculate each individual exterior angle. All right, so the answer is with the dot product. So if you, just a brief introduction to the dot product, if you have two vectors, v1 and v2, and v1 has a coordinates of x and y, and the second one has coordinates x and y, then I can calculate the angle between both of them. So and the dot product equation goes like this. So if we have v1, the vector v1 times vector v2, so this dot here is the dot product, denotes the dot product, equals the magnitude or the length of the first vector times the length of the second vector times the cosine, cosine the angle between both of them. I can evaluate the cosine theta from this equation, and I can get this left side, v1 times v2, over the magnitude of these two vectors. So the numerator here, the dot product of these two vectors is the x of the first times the x of the second plus y of the first times y of the second. Now divided by, the denominator here is the lengths or the magnitudes of these two vectors, and it's the square root of the x squared plus y squared of the first times the square root of the x squared plus y squared of the second. Calculating this, I will get the cosine of the theta, or the cosine of this angle. However, I want theta, and I think that's straightforward. You just take the inverse of the cosine of this value, and you will get what theta is. Now I will apply exactly the same idea here, the same principle, on all of the vertices of the irregular trapezoid I have. So here I have 4 vertices, v1, 2, 3, and 4, and I want to get theta 1, theta 2, theta 3, and theta 4. In this case, for example, for theta 1 here, I can get v1, the vector v1, directed to the right, and v2 directed upwards, and the dimensions or the coordinates of the first vector v1x can be calculated by the x of the second vertex minus the x of the first vertex. The y coordinate of this vector, of the first vector, is the y coordinate of the second vertex minus the y coordinate of the first vertex. The second vector is exactly the same. So the x coordinate of this vector is the x coordinate of the third vertex minus the x coordinate of the second vertex. The y here, the y coordinate of the second vector is the y coordinate of the third vertex minus the y coordinate of the second vertex. And so on and so forth. I can go apply exactly the same thing on all of the other sides. In this case, just by applying the inverse of the cosine of all of these values here, I can get what the external values or the external angles of this irregular polygon. All right, now I got the exterior angles. I need now to get the interior ones, phi 1, phi 2, phi 3, and phi 4. However, I know that any interior angle plus the exterior angle, they both add up to 180. So these two add up to 180, these two the same, these two the same, and these two the same. So phi 1 plus theta 1 equals 180. And I think it's very straightforward here to solve for phi 1. which is 180 minus theta 1. All right, now the question here is now how to code all of this. So how to construct an irregular polygon and how to calculate the lengths of the sides, how to calculate the exterior angles and the interior ones. For this, we need to move to MATLAB. So let's go to MATLAB now. All right, now this is MATLAB and we always try to start MATLAB with 3 lines, which are clear all, that clears all previously assigned variables, close all, which closes all other opened plots or figures, and CLC, which will delete everything in the command window, make it disappear, just to declutter your screen. All right, so let's start by defining the coordinates of the vertices of your irregular polygon. All right, so first let's define the coordinates of each vertex of the irregular polygon. For this, I'm gonna just denote the SX, which is the X coordinates, and the SY, I'm gonna denote it, which is the Y coordinates. All right, so the X coordinates here, I'm gonna start with minus 0.9, for example, and then 1, and then 0, and then minus 0.6, minus 0.9. You can change them later on for sure. So the Y of the first one is minus 1, and then minus 1 for the second. And for the third is 1. For the fourth is also 1, and for the fifth is minus 1. All right. Now the number of the sides or the vertices is that, I'm going to call it invert here, is the length of the SX minus 1. So you can see here that we have 5 points. The reason is that I need to add the last one so MATLAB can know to go back to the original point. So I start with 1 point, I need to go back to the same point. So this needs to be added at the end. All right, let's visualize the polygon, see how it looks like. So first I need to construct a figure, and then I need to plot the SX and SY in blue and in a line width of, for example, 1.5, and then let's go for X label here, which is X, and the Y label, which is Y. So let's maybe we can add the grid on as well, just to see how it looks like. All right, let's run this and see how it looks. Here we go. It's taking a bit longer than expected. Hopefully no complaints. Oh, okay. So this is the X label. Let's run it again. Okay. All right. So this is the same actually irregular polygon that we made our explanation on the PowerPoint before. So you can see here the X is from -1 to 1, the Y is from -1 to 1, and this is our irregular polygon. We know the vertices of each one. By the way, just to show you, if I remove the last bit here, MATLAB won't be able to go back to the first point. So if I run this again, you can see here that it starts from here, go upwards, and then stops there. So I need to tell MATLAB to go back to the original point. That's why I need to add the last 2 bits. All right, good. So now I have constructed the polygon. Let's now calculate the length of each side. So calculate the length of each sides. And for this, I need to go for the for loop because I need to go through all the vertices. So for I edge goes from 2 to the length of Sx. Let's go for L. L is the length. I edge. So this is here the square root so that it is the Euclidean distance. So I need to do the square root of the x's squared plus the y's squared, and here we have the Sx I edge minus 1 minus Sx of I edge, and the same for the sy, I edge minus 1 minus sy, I edge. All right, let's close the loop and let's see, hopefully no complaints here. And let's see what L equals to. All right, so you can see that the lengths are different. So this is 1.9 is the first side, which is on the bottom here, and then 2.2 is this one, the tilted one, and 0.6 is the smallest, the shortest length, and the left one is 2.02. Okay, good. So now we know what the lengths are. Let's move on to calculate the angles now. All right, now, first of all, I need to calculate the exterior angles between two vectors, or let's say two sides, for example, using the dot product. Okay? Now, I need to use for as well. Because before this, I need to calculate the vectors of each side, of each edge. So this is vectors of each edge, which are the V's as we denoted them in the PowerPoint. So for I goes from 2 to length of Sx, exactly the same thing. I need to calculate Vx first, the x coordinates of each edge. So this is I minus 1 equals to Sx of I minus 1 minus Sx of I. So these are the x, so here it's I. Okay, and I need to calculate Vy, which is exactly the same thing. So this is Sy for I minus 1, and then I have Si of 1. Not 1, sorry, it's I. Let's close this, so, and let's run just to make sure there are no complaints in what we're doing. Oh, okay, there is. Okay, this is length. Okay, and everything looks fine. Now let's go for another for loop to calculate the dot product. Now we want to calculate each external angle. So for j equals from 1 to length of Vx now. All right, not Sx. I need to go just through the vectors, the four sides or the four edges. I am going to denote a new variable which is GP. GP is j plus 1, all right, which is next edge, denotes the next edge. And I am going to say if JP here is larger than the length of Vx, then just put JP equals JP minus J, which means go back to the very first point or very first vertex. So this is Vx here. Okay. Now let's close the end. Close the if statement. And let's calculate the external angle, each external angle. So this is end of this. I have copied it before the video just to make sure there are no mistakes in my writing. So you can see here it's the a cos. A cos is the inverse of the cosine. And here we have vxj times vxjp. So this is the x of the first vector times the second, plus the y of the first times the y of the second, over the denominator here is the square root of the, which is the magnitude of the first vector times the magnitude of the second vector. All right, now let's run and let's see what are the external angles here. By the way, the external angle you will have are all in radians. So if you want to see them in degrees, you need to just here times, you need to multiply it by 180 over pi. And you can see here that it's 106. So the first external angle here is 116 degrees. The second one, 63 degrees. The third one is 81, and the fourth one is 98. These are the external angles. I want to make sure that the external angles, or the sum of the external angles that I got, add up to 360, just to make sure my calculations are right. So here the sum of all exterior angles, I know that the sum of exterior angles equal to the sum of what I have, so x angle here, and I want to see them as in degrees, so 180 over pi. All right, let's run and let's go and see what the sum of the exterior angles are. Will it be 360? If it is, then everything is going okay. It's 360. All right, perfect. So far so good. I got the exterior angles. Once I have the exterior angles, I think it's straightforward to get the interior ones, because each exterior with its interior add up to 180. So let's calculate the interior angles for all of the sides. So I'm gonna go for 4 theta goes from 1 to the length of exterior angle here. I'm gonna say it's the interior angle equal for each counting, for each theta here, equals to pi, which is the radian for 180, minus each of the exterior angle that I have, and this is theta. And let's close the end here. Okay, so let's run. And okay, we don't have exterior. We have, where is it? Yeah, it's right there. So we don't have the t. And let's go. All right. So this is the interior angles, and I'm gonna show them to you with degrees as well. So these are the interior angles: 63, 116, 89, and 81. Now, where is the, okay, so this is the figure, and starting from here, this is 63, and sorry, this is 63, and then 116 here, and 98 here, and then 81 here. So these are the interior angles. One last check that my work is okay. I need to calculate the sum of the interior angles, but now using the loop, or using the code that I'm using here. So I will say the sum of interior angles using the code equals to the sum of everything I've got here, all of the interior angles that I've got here. All right, and let's see them in degrees, just to make sure to make the reading easier. And also I want to calculate the sum of, sorry, the sum of the interior angles, but now using equation. Now I know that the sum of the interior angle, so this is equation, equals to the invert, which is the number of the sides, minus 2 times 180. Let's see if these two are equal. If these two are the same, so if the number from our code equals the number from the equation, then our code, I think, does what it should be doing. Let's run this and let's see what the sum of the interior angles resulting from the code, from our code, is 360. All right, let's go and see what the equation gives us. Also 360. So I think everything is doing what it should be. Last thing I want to show you here is that what if I have a triangle, an irregular triangle, irregular polygon as a triangle? We know that the interior angles, the sum of the interior angles is 180. So let's maybe try to confirm that everything that we are doing is actually right. So this is a new Sx and this is a new Sy. There's the Sx. Here I have -1, -1, 1, and -1. Let's comment these here and let's comment this here. And let's run all the code, but using this. So look at this triangle. And here you can see that we have this side equals this side, and this angle equals this angle. So let's make sure that everything is what it should be. Okay, let's go and see what the lengths are. So this is 2, and this is 2, and this is 2.8, which is what's it should be. If I go and let's go for the interior angles, and I want them in degrees to make our readings easier. And you can see here that you have 90. So where's my so this is my figure here. So this is 90 here, and this is 45, and this is 45. And the sum of the interior angle from the code equals to 180. However, from the equation, it should be exactly the same, 180. That's it for now. You can see the code that I used here in the GitHub link down in the description section below. If you have any other way of doing this code differently, please let me know in the comment section. Thank you very much, and I'll see you in the next video.